Hi, I'm David Purser. This is joint work with Marco Gaboardi and Kobbi Nissim. This paper considers the problem of verifying whether a loop-free program is differentially private. First, let us consider the concept of differential privacy. Consider a randomized mechanism which takes n input bits and outputs L bits. We say it is differentially private if given two inputs which we consider neighboring and any outcome, we require the probability distribution of the randomized mechanism to follow the following inequality. The inequality states the probability of seeing a particular outcome from the input x must be very close to the probability of seeing the output from input x prime. Here, these two inputs, x and x prime, are neighboring in the sense that they differ by one input. This inequality enforces that the ratio between the two must be bounded by a number close to 1, implying that if you see a particular outcome, it will be hard to distinguish whether it came from input x or x prime, because the probability of the two scenarios happening is very similar. The concept of differential privacy can also be extended with an additional parameter delta. This parameter, in addition to the parameter epsilon which controls the ratio, allows for some additive error. Often, an algorithm is accompanied by a proof that it satisfies differential privacy. However, this proof is usually created on paper. This can lead to some problems. In particular, these proofs are tedious to make, which can lead to mathematical errors in the reasoning. Even though the proof may be technically correct on paper, it may not be correct when translated onto a real computer. This is because real computers require finite values, finite precision, and a lot of algorithms require sampling from a continuous distribution, which cannot be done perfectly on such a real computer. Hence, the proof may not be technically correct on the real implementation. A lot of algorithms are built up using composition theorems. This allows basic building blocks to be composed together to derive the complete algorithm. The parameters can be worked out using a series of composition theorems, which allows bounds to be computed on epsilon and delta. However, these bounds, when composed together, may lose accuracy. This leads to conservative overestimates on the bounds epsilon and delta. In the next slide, we consider this particular issue further. Our approach aims to overcome all of these issues. By taking an automated approach, we avoid the possibility of human errors, and we conduct our verification on programs which can be implemented in practice. We also decide for specific parameters epsilon and delta without over-approximation. By studying the complexity, we place limits on the tractability of automated verification. As we remarked, it's well known that differential privacy admits compositional properties. So if M1 is epsilon 1 delta 1 differentially private and M2 is epsilon 2 delta 2 differentially private, then some mechanism which only accesses the underlying dataset through M1 and M2 is epsilon 1 plus epsilon 2 delta 1 plus delta 2 differentially private. However, this is not necessarily optimal. It's an over-approximation. If you have k mechanisms which are epsilon 1 delta 1 up to epsilon k delta k differentially private, when they're composed together, they're actually differentially private for a multitude of epsilon delta pairs. Mertag and Vadan show that it's sharp-p complete to compute one of the two parameters given the other. Even this may not be optimal when the individual components, when composed, do not behave in the worst case. For example, if M1 computes the average overall female salaries and M2 computes the average overall male salaries, then each of the two mechanisms operates on a separate partition of the data. In this case, we only need to take the maximum of the two parameters. There are several examples of algorithms where their parameters, epsilon and delta, are much lower than a naive, composition-based analysis of the algorithm would lead to. It's therefore important that our verification procedures do not solely use composition-based reasoning. We address these issues by taking a white box approach. So we test a specific mechanism where we have full visibility of each of its subcomponents satisfies a certain level of differential privacy. This allows us to test the true bound, rather than the worst case over-approximation. We conduct our analysis on probabilistic, loop-free programs. Here, we allow numbers that are integers, but we only allow for integers using a finite representation. So, for example, we allow integers which can be represented with k bits. We have standard Boolean operations such as AND and OR, and integer comparisons. Whilst we have the literals true and false, we also have a new command, random, which either returns true or false with probability 1/2 each. Similarly, we have the standard integer operations, addition, multiplication and subtraction. but on top of that we have a sample command which can sample uniformly from the space of integers. Our standard program commands include variable assignments, sequential composition, and branching, but crucially, no loops. Our final program is put together by taking a series of variable inputs, a sequence of commands, and returning some of the variables that have been allocated during the execution of the program. Note that the program has a finite input set, a finite number of commands, and a finite output set. Hence, all of the problems will be decidable. The only question is what is the complexity. We note that it's equivalent to consider the Boolean fragment of this program. Integers of a fixed size can be represented with a fixed number of Booleans. Indeed, the operations on them will become more complicated, but only up to a constant factor. We note that the standard probabilistic programming operator, which conducts two branches with probability 1/2 each, can be simulated using if random, then C1, else C2. Finally, we note that programs in this class can be converted into a randomized circuit. A randomized circuit is simply a Boolean circuit where a certain set of the input is decided using coin flips. This generates a probability distribution. The probability of a particular output on a given input is simply the number of allocations to the random bits which lead to this outcome divided by the total number of possible allocations to the random bits, which is 2 to the m. There is an equivalence between randomized circuits and probabilistic loop-free programs. This means any loop-free program can be converted into an equivalent circuit in polynomial time. Similarly, any randomized circuit can be converted into a loop-free program. This is easy to see. The output of each gate can be assigned to a variable, then each such assignment can be ordered according to the topological sort of the circuit. Here is a trivial example of a randomized program and its equivalent circuit. This example takes as input x and flips it with probability 1/4. This is because x and not r, or not x and r, is equivalent to the exclusive OR between x and r is true with probability 1/4. This is a particular case of randomized response, which we'll look at later. This example program turns out to be ln3 differentially private. That is, differentially private with the parameter epsilon equal to ln3, or e to the epsilon being 3. Because of the equivalence between our probabilistic loop-free programs and randomized circuits, we work entirely in the space of randomized circuits. We show that deciding whether a randomized circuit satisfies epsilon differential privacy is coNP with a sharp p oracle complete. However, for epsilon delta differential privacy, we do not show completeness. The hardness result translates because epsilon differential privacy is a special case with delta equals 0. However, in the case of epsilon delta differential privacy, we can show it can be decided using a coNP with a sharp p oracle, which itself has access to a sharp p oracle. In the case of black box composition, we saw that computing the optimal parameters is sharp p complete. However, it was also shown that approximating the parameters can be done using a polynomial time approximation scheme. However, we show in the white box setting that this problem is NP hard, and therefore there does not exist a polynomial time approximation scheme, unless p equals NP. So, as a reminder, NP is the complexity class of problems which can be solved using a non-deterministic polynomial time Turing machine where at least one run must accept. The complete problem here is satisfiability, where given a Boolean formula, you require at least one assignment to the variables results in the formula being satisfied. The complement, coNP, requires that all runs of a non-deterministic Turing machine accept, and tautology is complete for this class, where the formula must be satisfied for all possible assignments. Sharp p is the counting analogue of these problems. It's not a decision class, but rather a functional class, where it returns how many of the runs accept. Another thing to remark here is that the class coNP with a sharp p oracle is equivalent to the class coNP with a pp oracle, and so our results could be rewritten using coNP with a pp oracle. Let us now show that deciding epsilon differential privacy can be done in coNP with a sharp p oracle. Recall the definition of epsilon differential privacy shown on the right. This is a slightly different form. Instead of quantifying over all subsets of events, you only need to quantify over singleton events. The program first guesses two inputs which are neighbouring and an output which are candidates for violating differential privacy. To compute these numbers a and b, probabilities need to be computed, and this is done using a sharp p oracle. Intuitively, a sharp p oracle can ask how many allocations to a circuit result in a particular outcome. Then note that the underlying circuit is differentially private if all runs of this program accept. If a single run rejects, then it is not differentially private, as a violation has been found. Recall that NP requires just a single run to accept, and because we require all runs to accept, this is a coNP procedure using a sharp p oracle to compute the probabilities. However, we will next show that its coNP with a sharp p oracle complete. To do this, we'll use IMAGSAT as the underlying reduction. However, we'll actually use its complement, AllMinSat, which is a coNP with a sharp p oracle complete problem. Here, you're given a Boolean formula. Note this is a formula, not a circuit, which takes n plus m variables. So the input variables are partitioned, some which are denoted by x and some which are denoted by y. Here it requires that there is some allocation to the x variables, such that over half of the allocations possible to the y variables result in the formula being satisfied. And in the complement, we require the opposite, so that all of the allocations to x requires at most half of the allocations to y result in the formula being satisfied. And so given any such formula, it either falls into IMAGSAT or into AllMinSat. Now our reduction will distinguish between the two cases. We will encode AllMinSat using randomized response. Suppose you're asked an embarrassing question and you may not wish to give the true answer. However, you may be prepared to give a randomized version of your answer. Suppose you flip a coin. The coin flip will tell you either to tell the truth or to lie. Using a perfectly random coin, this will tell you to tell the truth with probability 1/2 and to lie with probability 1/2. This gives total privacy but no utility. In the other extreme, suppose it tells you always to tell the truth and never to lie. This gives no privacy, but the answer has full utility. For a range in between this gives a range of privacies. For example, if you tell the truth with probability 3/4 and lie with probability 1/4, the person receiving the answer has some confidence in the answer, but you have plausible deniability that actually your answer was a lie. Setting p equal to 1 over 1 plus e to the epsilon gives an epsilon differentially private mechanism. To encode this, we'll use a circuit which has a single input bit, z, and will allocate probabilistically both x and y. Now suppose you output both x and z, but z is going to be flipped or inverted according to the outcome of the formula. Note that if the formula is in AllMinSat, then z has been flipped between 0 and 1/2 of the time, as for no matter the choice of x, all of the allocations to y result in the formula being true less than half of the time. This isn't quite what we want, so instead we'll skew the result with a new fresh random bit p1 so that we flip the answer between 1/2 of the time and 3/4 of the time. This is because either p1 will be true half of the time, or p1 will be false half of the time, but the formula will still be true up to half of the time. Again, this is not quite what we want because now we flip the answer too often. So we invert this. So in fact we will flip the bit between 1/4 of the time and 1/2 of the time. Recall that flipping the bit between 1/4 of the time and 1/2 of the time is the region of most privacy. In the converse, if the formula is in IMAGSAT, then z is only swapped between 0 and 1/4 of the time. This means the bit z isn't flipped often enough. So this circuit is ln3 differentially private if and only if the original formula was in AllMinSat. This is achieved by setting 1/4 equal to 1 over 1 plus e to the epsilon. Hence, deciding ln3 differential privacy is coNP with a sharp p oracle hard. Let us now turn to deciding whether a circuit is epsilon delta differentially private. Recall the algorithm for deciding whether a circuit is epsilon differentially private. The natural extension is simply to alter the inequality to incorporate the plus delta requirement. However, this algorithm is not correct. For epsilon delta differential privacy, it is crucial that we test over all subsets of outcomes. However, whilst this algorithm is now correct, it is not possible to write a set E down in polynomial time. This is because the set E could be of exponential size. Instead, we provide a different algorithm which solves the problem in coNP with a sharp p oracle, where that sharp p oracle itself has access to a sharp p oracle. To do this, we'll reformulate differential privacy. Recall the original definition. Let's first take the second probability over to the other side of the inequality. Let's also re-express this inequality as a sum. It's clear this inequality must hold for all subsets E. In particular, it must hold for the worst case E, i.e. the E with the largest sum. So we can consider for each output whether it contributes positively to the sum. This leads to the following definition, which does not quantify over E. Using this reformulated definition, we want to compute this sum for some fixed x and x prime. As things stand, this sum is a rational number between 0 and 1. However, by renormalizing, we can make this sum an integer. If we let e to the epsilon be a rational number, u over v, we can then multiply by v times 2 to the m. This normalizes the denominators in the probabilities and v. So this sum is now an integer between 0 and 2 to the m plus log v. Intuitively, we'd like to compute this value, but we're not going to do this. Instead, we're going to create a non-deterministic Turing machine which has this many accepting runs. We'll first consider how to do this for a fixed output O. With a sharp-p oracle, we can compute this value. However, we can then spawn off 2 to the m plus log v runs and ensure that the correct number accept. To do this, we compare the run number with the answer. So, for example, if the answer should be 3, the first 3 runs will accept. If the answer is 4, the first 4 runs will accept. We can then repeat this procedure for each possible outcome. Thus, we have the correct number of accepting runs as this sum. We now have a non-deterministic procedure which for a fixed x and x prime produces the same number of runs as this sum. So to decide differential privacy, we need to test for each x and x prime. We're going to produce a coNP with a sharp-p oracle with a sharp-p oracle procedure to test differential privacy. The first step is to choose x and x prime, which are neighbouring, as candidates to violate differential privacy. Then construct a copy of M, but with x and x prime fixed to the chosen x and x prime. This new machine, M hat, has no inputs. Since M is a non-deterministic polynomial time procedure with access to a sharp-p oracle, asking how many runs it has complexity sharp-p with a sharp-p oracle. We therefore ask how many runs M hat has, and compare this with v times 2 to the m times delta. The circuit is differentially private if all runs accept. If any one run rejects, then it is not a differentially private circuit. As we require all of the runs to accept, this is a coNP procedure. In conclusion, we've shown that epsilon differential privacy is coNP with a sharp-p oracle complete. For epsilon delta differential privacy, we've shown it's coNP with a sharp-p oracle hard, and it can be decided in coNP with a sharp-p oracle which itself has access to a sharp-p oracle. In the case of epsilon differential privacy, the input and the output are both resolved by coNP, and the probability is resolved by sharp-p. In the case of epsilon delta differential privacy, the output cannot be resolved inside coNP, so the coNP resolves only input, the first layer of sharp-p resolves the output, and the last layer resolves the probability. We also show it's NP hard to approximate epsilon given delta. The result proceeds similarly to the hardness result already shown. The remaining open question is to close the complexity gap for epsilon delta differential privacy. Is it coNP with a sharp-p oracle complete, or coNP with a sharp-p oracle complete, or complete for a class in between?